Okay, so the next thing that we have here is exercise 16.2, which is a couple of examples related to, I suppose, events and types of events and that sort of thing. So question number 1 is a dice is rolled, let E be the event. I suppose that means that the dice is rolled once. So that means that the experiment is you throw a dice. And let E be the event dice shows 4 and F be the event the dice shows an even number. So we have an event E. We have an event E that the dice shows basically 4, and event F which is basically the dice shows an even number. The dice shows an even number. So that these are the two events. Are E and F mutually exclusive? We want to know if E and F are mutually exclusive. E and F mutually exclusive. So mutually exclusive, that means that they cannot happen together, meaning that basically basically I forgot the notation here. Mutually exclusive events where basically if meaning that you can say that, for example, E of I, the intersection of E of I and E of J, you can say that the intersection of E of I and E of J is equal to the null set for I is not equal to J if for n events E1, E2, E3 and all the way up to E of n. That means that if you have n events as E1, E2, E3 all the way up to E of n, the intersection of E of I and E of j for I is not equal to j, any two events, if you take any two events, those events should not be, the intersection of those events must be the null set, meaning that the events must have basically no outcome in common. So now let's see if that is the case. So that is our condition, and basically the experiment of throwing a dice is basically the sample space for this experiment is basically 1, 2, 3, 4, 5, and 6. Now the event E, which basically says that the dice shows a number 4, that would be just this number 4 here. And the event F, is the dice shows an even number. If the dice shows an even number is, then you have basically either a 2 or a 4 or a 6. Right? So now, since the intersection of E and F, the intersection of E and F is equal to, is basically, is a set that contains a 4 which is actually equal to E. That means that then, since it's not equal to the null set, then you can say that the events E and F, are not mutually exclusive. Now I want to, let me take a look at the answer here. Okay, now additionally what I want to do is that I want to find the answers on tiwari.com. So you can go over here, and this is 16.1, I suppose. So you can see that you can go over here to tiwari.com. Let me go to the web today. If you go to the home page of this website, you can see that you have class 11 over here, and then you have mathematics. So then in mathematics chapter 16 probability, and then you can go over here, so you see 16.2, 16.3, then the miscellaneous exercises and so on and so forth. So if I download these exercises in PDF, I will get the answers over here, which is a great thing about these books, is that you can easily find the solution sets, not mathematical solution set, but the set of solutions of these books, many basically different websites on the internet, because, well, they are very popular, these books, because mainly India is, I mean, academically they are very competitive, which is a strange thing, but that's the case. And so many persons and many individuals and many companies, and well, they have basically provided all of these solution sets. Now, of course, we already solved this problem, but there is something about these solution sets. When you read them, there is usually interesting and useful pieces of information and different ways of solving the problem that you can learn here. So that's something that it doesn't hurt really to go through the solution once, even if you know the solution. So I put this over here, and then let's get to the second question here. Okay, so the second question here is, let me actually go through the solution here. Okay. Okay. Now the second question here is question number 2. Which is the dice is thrown, describe the following events. So when basically a dice is thrown, you want to describe the following events. So your sample space would be basically 1, 2, 3, 4, 5, and 6. So a number less than 7. So the event that you get a number less than 7, a number less than 7. So a number less than 7 would be basically would be a set A, which is 1, 2, 3, 4, 5, 6, and that's equal to S. So now I don't know in what way I'm supposed to describe these events. Okay, it seems that you're supposed to you're just supposed to write basically the events. That's all that you need to do here, as it seems. And number two is a number greater than 7. A number greater than 7 would be basically event B. A number greater than 7, and that would be basically a set B, which is an empty set, which is also the null set. This is also the kind of notation that you can use for the empty set. Part 3 of the question is a multiple of 3. So C would be a multiple of 3. So that would be C would be equal to basically 3 and 6. Would be 3 and 6. And D would be basically a number less than 4. A number less than 4. So a number less than 4 would be 1, 2, and 3. Basically, event E would be an even number greater than 4. An even number greater than 4. Greater than 4. So then E would be basically 6. And F is the event that a number not less than 3. A number not less than 3, meaning a number greater than 3. And that would be basically 4, 5, and 6. Now what we want here is, for example, find the union of A and B. We want to find the union of A and B. So A union B would be equal to basically the union of this set with the null set, which is the set itself. So it would be basically again equal to the set 1, 2, 3, 4, 5, and 6 union with basically the null set, which is equal to 1, 2, 3, 4, 5, and 6, which is equal to S itself, and of course this is also equal to S. And instead of this, of course, you can write the null set. Then you want to find, for example, the intersection of A and B. So you know that the intersection of these two sets would be the null set, because they have nothing in common. The union of B and C. The union of B and C would be again, basically you have these two sets, and B is a null set, so you get this set at this set, basically the set C itself, or event C itself. So you will get 3, 6. And then you have the intersection of E and F. The intersection of E and F is basically, so E is basically this set which has only one member 6, and over here you have 4, 5, 6, so the intersection of these two is what they have in common, which is basically 6. Now you have the intersection of D and E. The intersection of D and E is equal to, the intersection of D and E is actually equal to the null set, because they have nothing in common. So that is equal to the null set. And then you have the A minus C. You have A minus C. So A minus C is basically all the members of A, and you have to subtract from that the members that you can find in C if they have those members in common. So you have 1, 2, 4, 5, right? 1, 2, 4, 5. 1, 2, 4, 5. You have A minus C. And then you have D minus E, for example. D minus E. So D minus E is all the members that you can find in D, and you have to take away from that the member that you have here, but I don't actually remember the exact definition of subtraction here. So let me take a look at the solution. D minus E is 1, 2, 3. So D minus E is basically again now since you cannot find 6 in this set, then you will get the set D itself, meaning that you will get 1, 2, and 3. 1, 2, and 3. But for example, in this case, as you saw, we had A minus C. Let me close this window. Okay, so here basically, here we had A minus C. So A minus C is nothing but basically all of these members, and you have to take away all the members that they have in common between A and C. So they have, of course, 3 and 6, they have these two sets they have in common, so you would take these two members out, and then you will get 1, 2, 4, and 5. That's what we got. But now, I suppose we can actually go here and take a look at the difference of two sets. Let's see what the definition, because I don't actually remember that. Okay. Yeah. So the difference of two sets, first of all, you can see that it says that basically this has been written in 2018. The difference of two sets written A minus B is the set of all elements of A that are not elements of B. The difference operation along with union and intersection is an important and fundamental set theory operation. And the description of the difference, and if you want to understand it, these are called Venn diagrams. So in these Venn diagrams, you see that basically this set over here is A, and this set over here is B, right? And they have basically this part in common, which is A intersection B. Now, A minus B is basically this highlighted part over here, which means that all the members of A, except for the members of A that A and B have in common. That's basically all that it means. And from this diagram you can see that very, very easily. And of course the order is important, because A minus B is basically this highlighted part over here. But if you wrote, for example, B minus A, then B minus A would be this part over here. Just B without any of these parts, right? So that is that, and we have the complement. The complement is basically something that you also need to be familiar with, and that is one sort of difference is important enough to warrant its own special name and symbol. This is called the complement. One sort of difference is important enough, okay? And this is called it's used for the set difference when the first set is the universal set. So the complement of A is given by the expression U minus A, and this refers to the set of all elements in the universal set that are not elements of A, since it's understood that the set of elements that we can choose from are taken from the universal set. We can simply say that the complement of A is the set comprised of elements that are not elements of A. So the complement of set is relative to the universal set that we are working with, for example, A is equal to 1, 2, 3 and U is equal to 1, 2, 3, 4, 5. The complement of A is 4 and 5. And it's our universal set. If our universal set is different, say for example this set here, then the complement of A would be, for example, 0, -1. I don't know where I think this is wrong. Always be sure to pay attention to what universal set is being used. Now, notation for the complement. So the word complement starts with the letter C, and so this is used in the notation. The complement of set A is written as A superscript C. So we can express the definition of the complement in symbols as the complement of A is equal to U minus A. Is equal to U minus A, and another way that is commonly used to denote the complement of a set involves an apostrophe, which is A prime. Other identities involving the difference on complements are these, and well, this is a whole lot of things that you would learn in the algebra related to these sets, which we haven't really done here. But I suppose for now, I think it suffices to say that, for example, when you have A minus B, from the Venn diagram, you can easily see that, and very clearly see that if this is A and this is B, and they have this part in common, which is A intersection B, this part, meaning that then A minus B is basically all the members of A except for actually A intersection B. So this part you take it out, and then this becomes A minus B. So that's the whole story here. I had actually forgotten this. So, and of course, if there is no part in the intersection of the two sets, then there is no part, and then you will get the set A itself. And so that's basically that. Now, the next thing that we have here is E intersection F prime. And F prime, I suppose, is the complement of F. F prime is the complement of F. So here we have E intersection F prime. So E intersection F prime is the intersection of the set A and the complement of F, if I'm not mistaken. Let me take a look at this. Okay, so you saw that basically when we were reading that this website written by basically the website that we were reading about, A minus B, there was something called a universal set, right? So this universal set is basically the set that when you're talking about a situation, any sort of situation, all the sets that you're talking about, there is one set that becomes the universal set of all of those sets. For example, in the case of this situation over here, which we have the sample space 1, 2, 3, 4, 5, 6, then in basically using the Venn diagram, this is your universal set, this basically rectangle here. And in this universal set you have 1, 2, 3, 4, 5, 6, and that is, for example, your set A, for example, right? So, for example, if you write 1, 2, if I write, for example, set A over here, I can show it this way, and I can write 1, 2, 3, 4, 5, and 6. And then, for example, set, I don't know, set, now over here what we want to calculate is for example, E intersection F prime, for example, E intersection F prime. And the set F over here would be 4, 5, and 6. So 4, 5, and 6 is basically set F, right? So I can write this as set F this way as 4, 5, and 6. Now, the complement of this set F, as we noticed before, is basically all the elements is always relative to the universal set, right? So what that means is that when you write F prime, or when you write the complement of F, that is basically all the elements that you can find in the universal set except for the elements that you can find in F, which is basically, in this case, for example, 1, 2, and 3. 1, 2, and 3. That is basically the complement of a set. And what that means is that, for example, if you have this universal set over here, call it U, and in this universal set you have, for example, only one set A, for example, 1, 2, 3, 4, and 5. Let's call this set A, for example. If you have this set A and this is the universal set, which is again the same thing, meaning that A is equal to 1, 2, 3, 4, and 5, and U is equal to, or the universal set basically is 1, 2, 3, 4, and 5, then the complement of A is basically the null set. The complement of A is the null set, because now you're looking at all the elements that are members of the universal set except the members except for the elements that are members of A, which would be nothing. So that would be the null set. So now what that means is that in this situation, our universal set is actually the sample space. Basically our universal set is of course the sample space, because your sample space is the set that contains all the possible results, or what do you call it? All the possible I don't get the word. All the possible, basically every possible result of this experiment. Now you know what I mean. Now, so my universal set over here would be U, and let's say that basically there is a set over here. For example, there is a set over here E, which is basically, there is a set over here E which is just has a 6 in there, and there is also a set F in here which is 4, 5 and 6, which is 4, 5 and 6. So that is F, right? And you have also other things here as well, B, C, and so on and so forth. But now let's concentrate on these two, meaning that when you get, basically, let's say that you have 4, 5, and 6 here, and that is the set F. And then let's say that set E is basically this only this one element here, and this is your universal set. Now when I write basically E intersection F prime, these are, by the way, very important. I mean, the algebra of these sets is very, very important. We will hopefully, I don't know really, but hopefully we will sometime review them, because clearly I have forgotten a lot of them myself. So then what that means is that now E is basically, you know that it has just one element, which is 6. Now F prime, you know that F is basically 4, 5 and 6. So F prime is is of course the complement of F, and is basically all the members of the universal set that are not in F, which is nothing. So that is the null set. So you're taking the intersection of E, which is only a 6, with the null set, which is the same thing as the null set. And I suppose that is the answer here. Let's see. I suppose E intersection F prime is the null set. Okay. And then there is one more, and the F prime we already talked about it. Okay. So the next thing that we have here is question number 3, which we will also do. Okay, so the next question is question number 3, that says that an experiment involves rolling a pair of dice and recording the numbers that come up. So you basically roll a pair of dice recording the numbers that come up. Describe the following events. the sum is greater than 8, B, 2 occurs on either dice, and the sum is at least 7 and a multiple of 3. Which pair of these events are mutually exclusive? So if you... Now there is an event, there is an event A that says that the sum is greater than 8. The sum is greater than 8. Now, before I do this, I need to write the sample space of this experiment. And the sample space of this experiment is when you roll a pair of dice. Of course, you could get basically, it's just like the situation that we had before, meaning that you had, let's say that, call it, for example, dice number 1, and call this dice number 2. You have 2 dice, and the outcomes of this experiment are 1, 2, 3, 4, 5, and 6. And the outcomes of this experiment are 1, 2, 3, 4, 5, and 6. So then over here, for example, you could get 1, 1, or 1, 2, all the way up to 1, 6. And then over here, you can go all the way up to 6, 1. And over here, you can go all the way up to 6, 6. So that is basically, and you have all of these numbers over here. Now so this is basically, you have 36 elements here, and this is your sample space. This is your sample space. Now, having this sample space in mind, we have these three basically events here, which is the sum is greater than 8. The sum is greater than 8 would be basically, for example, over here the sum cannot be greater than 8 because you can go all the way up to 6 plus 1, which is equal to 7. And then 2 and 6 would be 8, which is still not greater than 8. And basically 2 and 5, which is 7. So the first 2 rows, we don't have any we do not have any results of this experiment. Result is not the right word to use here, but I'm using this instead of the actual word that I keep forgetting. So all the way up to here, we have no well, now I realize that words are actually good things, because if you didn't have them, you couldn't actually talk about anything. The outcome. So we have basically none of these outcomes would actually, in the language of probability, the right way of saying that would be none of these outcomes in the first 2 rows is going to basically favor this event. So then, for example, 3 and 4 is equal to 7, 3 and 5 is equal to 8, and 3 and 6 is equal to 9. So the first one over here would be 3, 6. So this one would be the outcome that would basically favor this event. And then when you come to 4 and 4 is 8, 4 and 5 is 9. So 4, 5 is also one such candidate. And 4 and 6 would be 10, which is also which is also the suitable outcome here. So we have, so far we have these three, and you want it to be greater than 8. So 6 and 1 is 7, 6 and 2 is 8, 6 and 2 is 8. So you have 6 and 3, 6 comma 3. You have 6 comma 4. You have 6 comma 5, and you have 6 comma 6. So you can write this set as basically 3 comma 6, 4 comma 5, 4 comma 6, and you have 6 comma 3, you have 6 comma 4, you have 6 comma 5, and you have 6 comma 6. 6 comma 6. So that is basically the event A. Now event B, clear this up, and this is all the way up to 6 comma 6. And I don't like this color actually. Now the event B that we have is 2 occurs on either dice. 2 occurs on either dice. So if 2 occurs on either dice, what that means is that, so you get a 2 here and you get a 2 here, and then there is no other way, there is no other outcome that would favor that event. So there you would get only 2 comma 2, and that would be B. And event C is the sum is at least 7 and a multiple of 3. So C is the sum is at least 7 and a multiple of 3. So if the sum is at least 7, then you have to basically 2 and 5 is 7, right? 2 and 5 is 7. So 1 and 6 is 7. 1 and 6 is 7, but it's not a multiple of 3. Now 2, 4 is 6, 2, 5 is 7, again not a multiple, and 2, 6 is 8, and not a multiple of 3. So then you have 3, 4, 7, 3, 5, 8, 3, 6, 9. So that is one thing, for example here, 3 and 6. 3 plus 6 is equal to 9. It's at least 7, the sum of them, and it is a multiple of 3. So that is one outcome here that we can pick. And then you have 4 and 3 is 7, so 4 and 4 is equal to 8. 4 and 5 is equal to 9, so you can get 4 and 5. And 4 and 6 is equal to 10, which is another multiple of 3. So 5 and 4 is equal to 5 and 3 is 8, 5 and 2 is equal to 7, 5 and 3, 8, 5, 4, 9. So 5 comma 4 is also there, 5 comma 5 is 10, 5 comma 6 is equal to 11, which is not going to help us. Then you have 6 comma 1, 6 comma 2, 6 comma 2 is 8, 6 comma 3 is equal to 9. So you have 6 comma 3, 6 comma 4 is 10, 11, and 12. That is also helpful. 6 comma 6. So the outcomes that would favor this event would be basically C is equal to 3 comma 6 and 4 comma 5 and 5 comma 4 and 6 comma 3 and 6 comma 6 and 6 comma 6. That's basically all that we need here. Now what we need to do here is that the question that we want to answer here is which pairs of these events are mutually exclusive. So which pairs of these events are mutually exclusive. So to know that basically mutually exclusive, what that means is that the intersection of the two sets or the two basic events has to be the null set. Or you could say that, meaning that there is no way that these two events could happen simultaneously. So for example, if I take, you can see that 2 comma 2 is not here. So then of course you can say that A and B are mutually exclusive. Also B and C are mutually exclusive. But C and A are not mutually exclusive because you can see that, for example, 3 comma 6 is a member of both of the events. So A and B are mutually exclusive, and also B and C are mutually exclusive, which is the answer. Number 3 is A and B and C are mutually exclusive. Okay, so question number 4 is 3 coins are tossed once. So you have 3 coins are tossed once. 3 coins are tossed once. Let A denote the event 3 heads show, and B denote the event 2 heads and 1 tails show, and C denote the event 3 tails show, and D denote the event a head shows on the first coin. Which events are mutually exclusive, simple, and compound? Okay, so we need to write the sample space of this experiment. So if you toss 3 coins once, 3 coins are tossed once. So that means that you have basically a first coin. Let's call it the first coin, for example, the second coin, and the third coin, and if that's the case, then basically on the first coin you could get either heads or tails. On the second coin you can get either heads or tails, and again heads or tails. And so you can basically get each of these different, you can get basically either heads or tails on each of the coins. So now if you want to basically put these 3 together, the easiest way is that, for example, you can put these 2 together first, and then put those together with the last one. Meaning that here basically you get HH, for example, HT, and then you will get, for example, TH, and then you will get TT. And now that you have these 4, you can put them together with these two, meaning that you can take this one with each of these two, take this one with each of these two, and so on and so forth, and you would get 4 times 2, which is equal to 8 different outcomes, which is basically then your sample space would be equal to H would be H would be HHT would be HHT would be basically HTH, HTT, HTH, HTH, HTT, HTT. I'm going to omit the commas because they're not really required here, right? So this is, for example, HHH and HHT, and so on and so forth. And then you have two forens, basically THH, you have THH, you have THT, you have THT, you have TTH, you have TTH, and you have TTT. Okay, so now that is our sample space. That is our sample space. And basically then what we need to do is we have basically a couple of events. We have event A, which is basically 3 heads show. You have 3 heads show, which would be basically A is equal to basically HHH, and except for that's the only member that this set has, or this event has. Then you have event B, which is denote the event 2 heads and 1 tails show. 2 heads and 1 tails. So 2 heads and 1 tails would be basically then B is equal to 2 heads and 1 tails, and what that means that these basically will show up. So 2 heads and 1 tails. And I'm taking that as probably exactly because there are, I mean, the best way to make sense of this statement is 2 heads and 1 tails show, and that's meaning that, for example, this would be 2 heads and 1 tails, 2 heads and 1 tails, 2 heads and 1 tails, and I think that's the only 3 members of this set, or of this event HHT, and then you have HTH, and then you have THH. You have THH, right? So that is basically B, and event C is basically 3 tails show. So you have 3 tails here. So then C is equal to, that would be only this TTT here. There is nothing else where you could get 3 tails. And then D would be a head shows on the first coin. D would be a heads on the first coin. On the first coin. So on the first coin, over here a head on the first coin, 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 and that's it. So you get basically D is equal to basically HHH, HHH, HHT, you have HTH, you have HTH, and you have HTT, HTT. So that's basically all the events that we have related to this sample space. Now we want to know which events are mutually exclusive. So mutually exclusive events are the kind of events where the two events cannot happen together, meaning that there is no outcome in your sample space that can basically ensure the occurrence of both the events together simultaneously. So what that means is that, for example, you see over here, I have A, B, and C over here, A, B, C, D over here. I have HHH over here, and I have HHH over here, right? So basically they have these, both of these events have this outcome in common. So what that means is that this outcome, which is ultimately can be found in your sample space, which is HHH over here, this can ensure the occurrence of both event A and event D, right? On the other hand, for example, these two events over here, A and C, one of them has HHH, one of them has TTT. So these are completely different events, of course, and there is no way that these two events can happen or can occur together, and there is no basically outcome in your sample space that can ensure the occurrence of both of these events simultaneously. That means that then you can say that, for example, A and C are mutually exclusive. So then mutually exclusive events would be, for example, A and C would be, for example, you see basically, for example, A and B are actually also mutually exclusive because they have no outcomes in common. So A and B would be also mutually exclusive. So A and D are not mutually exclusive because they have this outcome in common. And then you can check with B. So B and A are of course mutually exclusive. We have already written that, and the order of course doesn't matter here, whether you say A and B are mutually exclusive or B and A are mutually exclusive, that would be the same statement. So B and C are mutually exclusive. B and C are mutually exclusive, and then THH, HTH, so these two of course are not mutually exclusive. Then C and A are mutually exclusive. C and B are mutually exclusive, which I have already written. C and D are mutually exclusive. C and D are mutually exclusive. And of course then D and C are mutually exclusive. D and B are not mutually exclusive because of HTH and HTH here, and A and D are not mutually exclusive. So these four are mutually exclusive events. Now we talked about also some other type of event which is called a simple event. Simple events. So a simple event by definition was if an event E has only one sample point of a sample space, it's called a simple event. Meaning that, for example, C is a simple event, A is a simple event, A and C. And of course, these are not simple events because they have more than one sample point of the sample space. And there was something else called a compound event that we also talked about. And you can see that how these exercises are actually really necessary for anyone to learn mathematics, because without these exercises there's actually no way that you can learn mathematics. You have to solve exercises. Of course, you have to go through the theory and the definitions and everything, but then after that, if you don't solve the exercises, there will be a whole lot of gaps in your learning and you will not be able to use your mathematics anywhere, really. So a compound event, we said that if an event has more than one sample point, it's called a compound event. For example, B would be a compound event and D would be a compound event, B and D. So let me see if the question is all that it's asking. So that's number 4 is A and B, A and C, B and C, C and D. So A and B, A and C, B and C, A and C, B and C and D. Number 2 is A and C. Number 3 is B and C. B and D, I'm sorry. That's correct. So the next question that we have is question number 5. Question number 5, which is 3 coins are tossed. Describe 2 events which are mutually exclusive, 3 events which are mutually exclusive and exhaustive, 2 events which are not mutually exclusive, 2 events which are mutually exclusive but not exhaustive, 3 events which are mutually exclusive but not exhaustive. Okay, so here you need to write down your sample space, and then from there you can pick different things to demonstrate each of these events, basically. But I think we will end this video here, and then we will discuss this problem in the next video.